these slides are going to introduce you to some key points for setting up your electronics, some things I wish I knew, and then I include some examples, but I think the best path forward is if you have specific questions, you can ask them either today or moving forward throughout the semester. I'm happy to help support in that regard. So yeah, we'll do some quick tips, examples for what to sense, and then actually surprisingly it doesn't sound like there's many of you interested in IMUs, but generally speaking, IMU is a very commonly is a sensing modality of great interest for microgravity flight testing, so talk a little bit more of that. So in terms of preparing your documentation for your electronics, all of the documentation Ariel showed you, in my opinion, can be distilled to they just want to know that the plane can supply enough power to your experiment, that your experiment can safely operate at your expected current rate, and that if anything goes wrong, there's a quick way to shut off power consumption. So like most experiments like really easily meet these criteria, and there may be a few exceptions, maybe your ultra high voltage source would cause concern, but for the most part, I wouldn't worry too much about the documentation. So, as Ariel mentioned as well, there's normal AC wall supply available to you. So, if possible, and this is sometimes the case, you can power your electronics off of your computer and then just plug your computer into the available wall supply, and that's a very easy way to meet the criteria of zero-G core. Alternatively, you can power your device off of batteries, and that's also a quick way to meet power constraints. You will be asked, though, to make statements about your power supply consumption, so be sure to measure that. And my year, we had this concern because the stated outlet was not, in fact, a traditional wall supply, so we went all jumped through hoops to buy these like very specialized converters, which turned out to not be necessary at all. So. Good thing that you're not in the first year of deployment. So in terms of cabling, you're also going to be asked in the documentation to make sure that the cables that you select actually can support your power supply. Again, if your experiments are operating at like reasonable supply voltages, you don't really have to worry about this for anything under an amp or two, let's say. If you are running high power electronics, do make sure that the wire gauges that you're using are able to support those power rates. This is something that zero-G core cares about. And I'm showing you here just the standard wire gauge table.
I feel like I've seen a lot of different tables that give different numbers here. Is there a standard that they go by that you know they go by?
Oh, that's interesting. I was under the impression that there is a strict standard for what wire gauge corresponds to. Have you seen different tables?
Yeah, well, just like in a shower Google search, I've found different, and so I just chose the most conservative of the options available, and then I trusted that would be enough. But I didn't know if zero-G says, oh, use this chart.
Ideally, there's enough of a safety margin anyway in the wires that you're choosing that.
NASA does, zero-G doesn't. So we got a list from NanoRacks recently of what we can and can't use in terms of cabling for the ISS flight, but zero-G within the boundaries that you just described.
Well, maybe, is that public? Like maybe we could just use that, like you said, for NanoRacks, if that's
They gave us a range for very low power stuff, which is all of our boxes, but I can ask them for what the answer would be for yours. So send me a number of what you want, and I'll just ask them what the NASA answer would be.
Okay.
So yeah, don't cut it close, I think would be a reasonable answer to the question of maybe there's some variability in these tables. You're going to be asked to produce load tables as part of the documentation, which essentially boils down to measuring the current and voltage requirements for your experiment. So it sounds like there's a lot of general familiarity among this crew in electronics, but you can take these measurements using a standard multimeter by putting your multimeter in series and in parallel with your load in order to approximate the current and voltage consumption and produce those load tables. There were a lot of questions my year, though, about, for instance, determining the load of a laptop computer. And for something like that, looking up online just a coarse approximation for how much power your computer generally consumes seems to be sufficient for zero-G core. They didn't give us a hard time about these sort of approximations around consumption. Does anybody expect to be operating a very high power experiment?
What is very high power?
Let's say, tens of watts or more.
Anybody that I know in this year's selection.
Okay.
I think ours is about 25 watts.
Okay.
For the heated?
At the peak, without heat, just the DC motor. It's 12 volt
Yeah.
DC motor that sometimes takes 3 amps or 4 amps.
Yeah. You've been through this documentation before, though, a couple of times, so
They
I
had
expect.
yours as
Yeah.
high by their standards last year,
Yeah.
but interesting.
There's also a lot of scary documentation around kill switches, and this, again, Zero G Corp does have flexibility in this regard. All they want to see is that there is, in fact, a quick way to turn off your experiment if something goes wrong. So, like, you can use one of the traditional big red buttons, but you can also just state, for instance, in an experiment that's being driven by a laptop, that you could unplug your laptop or unplug the experiment from your laptop, and they were okay with that. Also, Ariel may have issued this warning at some point already. Okay. So our year, we had a very diligent engineer who used one of these traditional red buttons, and but unfortunately put it in a pretty vulnerable place on his experimental box. Meanwhile, another student who was doing a performance art piece accidentally kicked the red button during the flight and caused his experiment to abruptly stop mid-parabola. So, yeah, this is one of those warnings to to all of you to pay attention to the reality that the zero gravity flights are for sure guaranteed to be a chaotic experience, no matter how much preparation Ariel and Zero G Corp and others do. So just expect that people will be banging into your experiment and such. My main advice to you with respect to electronics and sensing is to make sure you put in as much time as possible this semester to make your experiment run as autonomously as possible, including actuation and data collection. One reason for this is if everything's automated, it's just more likely to work. But honestly, another reason is the zero gravity flight is so much fun, and it's worth it to be able to enjoy the experience yourself and have your experiment just doing its thing for the most part. Maybe you're supervising a little bit. So yeah, put in the work now. My recommendation. Some folks in previous years focused primarily on video capture. It sounds like all of you have already started putting thought into capturing sensor data, and that's good to hear. It's worthwhile. It makes this experience more valuable, both scientifically and artistically. So now I'll just run through some examples for what you might sense on the zero gravity flight, although we did hear from you guys as well. So my broad advice over the next few weeks is to really clearly articulate a research question or an artistic objective when you're determining what sensors you're going to integrate and what data you want to collect from them. So I'll run through these questions you might ask yourself, like what data would be useful to collect during the flight? For instance, if you want to be automatically triggering actuators as the flight is progressing. What data would be useful for post-flight analysis, either for an artistic video, maybe doing fun overlays, or for scientific analysis. And then a bunch of just honest questions about what actually could be tested or demonstrated on the ground, like what is actually unique about the zero gravity environment that you are leveraging that you strictly could not do, or you strictly could not run this experiment on the ground. And relatedly, what could be pretty easily and reliably modeled? Like, why are you, have you already modeled your system? And if you've chose not to model your system, is there some reason why experimental test is better than simulation? So I think just honestly asking these questions early in the process will make the flight more valuable to you. So any questions so far, or thoughts that have come up? So this is just high-level feedback. So I'll quickly run through a bunch of sensors you might consider. I've included a sample research question or artistic question that might incentivize you to use such a sensor. So you can use IMUs to track the angular rotation and position of your apparatus over time, which might help you track the motion of a unicycle, or last year we had somebody interested in the behavior of shrimp in microgravity, so maybe track their motion. You might, especially for any experiments interested in the motion of the body in this environment, you might want to make use of strain gauges to track posture or sort of any sort of muscular studies. Might make use of strain gauge for sensing bending force. Biological sensing, especially for folks interested in human behavioral changes or stress response in this environment. I'm showing here the empatico stress sensor, which is a sensor developed by one of the researchers here at the Media Lab. So, yeah, maybe you'd want to show how stress responses are changed based on how much exposure you have to microgravity, or maybe there's some type of interesting actuation for an artistic demo, like, yeah, maybe your stress response causes some sort of actuation.
God, I just want to make sure the mic's on. So we actually get
And we've had folks in the past interested in 3D printing and the behavior of liquids in microgravity, so perhaps you'd want to use some type of flow rate sensor, temperature sensor, moisture sensor. I mean, as you're all well aware, there's a large suite of sensors you might consider. And I believe, finally, if you're interested in pressure and vibration sensing, which can be very useful for understanding the noise levels of your environment, you can use piezoelectric vibration sensors. Many of you have probably seen these before, but there are ceramic discs that produce a voltage spike when subject to mechanical deformation, and there are also thin film piezoelectric sensors that can also perform similarly, show voltage spikes in response to mechanical deformation. So these are can be very handy for understanding the environment that your apparatus is working in. And I work extensively with piezoelectric sensors, so I can also answer questions over the semester on details of their use. So because I expect IMU sensing to be rather common, I wanted to include a little bit of additional detail on how you might go about using them. So for people come into a class like this with such a vastly different level of experience in electronics and sensing, so I think many of you will choose to use off-the-shelf sensing, like these prefabbed boards that you can buy off of SparkFun, and I think that's totally appropriate for a flight like this. I'm sure some of you in the room are fully intending to design your own boards and go all in on the electronics, and so you have to choose where you want to put your emphasis. But if you do choose to buy off-the-shelf sensors, you absolutely can go to websites like SparkFun and buy boards like this. And the IMU is handy because it incorporates both an accelerometer. Here you're looking at the inner workings of certain IMU accelerometers. You basically trap a small ball in a wall of piezoelectric film, and as the ball bounces around, the film will produce voltage spikes. So that's one way that IMU accelerometers work. And the IMU also includes an internal gyroscope, and what you're looking at here in an example of something called the Coriolis Effect. So you have this beam that's mounted on one side of this box, and as the structure rotates, the beam will continue to oscillate in its original, with respect to its original coordinates, and exert a force on the mounting point of the beam. So the measurement of that force is how the IMU goes about detecting change in angular velocity. But you don't have to go too far in the weeds to get one of these things working, especially if you want to make use of a SparkFun board and an Arduino board. You more or less hook up power, I2C communication buses, and an interrupt routine, and there's significant documentation online to get you going. But I did want to mention that for those of you who are more advanced or want to take the next step, there is definitely a lot more you can do to improve the quality of your sensor data. And I think, actually, just generally speaking, I think one of the tasks you might find yourself confronted with if you have multiple sensors in your experiment is, okay, you have these multiple data streams. How do you go about intelligently combining those data streams to make statements about how your experiment worked. Like, are you going to treat each sensor independently, or are you going to start to fuse them together? So in the context of IMU, you can see that this chip is actually drawing from two different sensor streams, accelerometer and gyroscope. And again, if you use chips like this, they often do all this work for you. So if that's the approach you want to take, then you can let the chip do it for you. But to give you an example of what sensor fusion might look like if you want to do it yourself, I include a little bit more detail on something called a complementary filter. This is showing you what is happening under the hood, often in code, for combining the accelerometer and gyroscope data. So what you're looking at is in Laplace notation, for those of you who are familiar, you're looking at you have some input angle, and you want to determine how that input angle is adjusted after some delta t based on the two streams of sensor data that you have coming in. And what you're seeing here are, again, Laplace notation representations for low-pass and high-pass filters. And the reason, let me actually skip ahead. So I think the key point to recognize is when your accelerometer data tends to have a bunch of high-frequency junk associated with it. Like all these squiggles are really just noise that you're not going to want to pay too much attention to. And so for that reason, it's traditional to low-pass filter your accelerometer data. Low-pass filter your accelerometer data to get rid of all this high-frequency junk. On the other hand, the gyroscope tends to give you these much smoother responses, but it has a problem of its own, which is that it tends to drift over time, which is going to show up as a DC bias, which means you're going to start getting this you're going to start getting this shift, this offset in your measurements, even if nothing is changing in your experiment. And so the way that you can get rid of that DC signal, which is really just like essentially a low frequency signal, is to high pass filter your gyroscope data. The first thing to recognize is that you want to low pass filter your accelerometer data and high pass filter your gyro data. And again, I'm assuming some knowledge of Laplace notation here, but these are the transfer functions corresponding to low pass and high pass filters, where the S, for instance, corresponds to like a first derivative, and tau corresponds to time constants. So maybe, I guess the key point here is that if you multiply together all of your, these are called H of S. If you multiply together all of the H of S functions that you're applying, you want to wind up with your original theta of S in order to show that that by applying these filters, you haven't actually changed the dynamics of your signal. You've just applied some filtering and merged the sensors together. So because this statement holds true, because the simultaneous application of a low-pass filter and a high-pass filter preserves our theta of S, this becomes an effective method for merging your sensors. In this term, there's a lot buried in this plot, but this term represents estimates of your noise associated with your accelerometer and gyroscope. So in addition to showing that you can low-pass filter and high-pass filter your data, get back your same result, you can also start playing around with understanding the noise that each of those sensors is going to contribute and what that does, what small effects that might have on your signal. So just to, I'll send out these slides. If you want to look at some of this more closely, if it's interesting to you, feel free. But I'm summarizing out what I just said verbally, which is we want to be able to apply a high-pass filter and a low-pass filter without adding additional dynamics to your system. The gyro angular velocity corresponds to S, because it's the first derivative. The angular tilt is just 1, because it's like just a displacement. And so you show that the transfer function does, in fact, equal 1. And this is the form that the complementary filter usually takes for merging angular and gyro data. There's a commonly used weighting function associated with the two. Okay, so anyway, that's a small peek at the type of thinking you could start to engage with, should you want to. And I hope I've also made clear that if you want to like just skip all of this and go to the Spark Fun sensor, that's cool too. Really depends on what your goals are.